Hello, everyone, and welcome to today's edition of our extremal and probabilistic combinatorics webinar. Before we start with the talk itself, let me quickly go through usual technical stuff. As you know, this talk is recorded, so if you don't want to appear on YouTube later on, just don't ask any questions in the recorded part. There will be at the end a part which will not be recorded. If you have any question during the talk, please don't hesitate to unmute yourself and pose the question, or if you have a problem with your audio or you don't want to appear online, then just write it in the chat and either the speaker will see it or I will read it out. And as usual in this seminar, at the end of the talk, there will be sort of a formal discussion, which will be part of the recorded video. And then I will at some moment switch off the recording, and either we can continue with discussing the contents of this talk, or we can just have an open chat. And now it's my pleasure to introduce our today's speaker, Andrey Kupavskii, who is at the moment in Grenoble. And Andrey will talk about the extremal number of surfaces. So Andrey, please.
Thank you, Honza. Thanks a lot for having me. It's a pleasure to give a talk at your webinar. So I'll be talking about the extremal number of surfaces. This is a joint work with 3 members of our lab in Moscow, this combinatorial and geometric structures lab, some of the other affiliations as well. So the 3 authors are Alexandr Polyanskii, István, Tomon, Dima Zakharov. Work would be about a problem in extremal combinatorics. Let me prepare the setup. And by the way, yes, as Jan said, don't hesitate to interrupt me if you have any troubles with the content. I'll try to go slowly, and we have enough time for questions. So what is the sorry, what is the setup? We are looking at comma f, where f is a family of R uniform hypergraphs, say. So by convention, of course, if we are looking at a family of R uniform hypergraphs, then we are working with an R uniform hypergraph ourselves. And the question, the question that we are asking is, what is the maximum number of edges in an R uniform hypergraph that does not contain a copy of any element, any hypergraph from this family F. So this quantity, right, maximum number of edges in an R hypergraph with no F from the family. So we are forbidding all the structures from our family and asking for this maximum number of edges. There are, of course, some classical examples, and classical examples deal with one element family. So the family that is consisting of one hypergraph.
One stupid question. May I ask, what does
Sure,
N
sure.
stand for?
Yes, sorry, of course. That's not a stupid question. Our hypergraph on N vertices, of course.
Thanks.
Yes. Yeah, this I should have written it. So R uniform and vertex hypergraph, no copy of hypergraphs from our family. Typically, of course, F is of size 1, as I said, but in our case, we'll be working with these families of hypergraphs that are homeomorphic to a given hypergraph. And what do I mean by this? When I say that two hypergraphs are homeomorphic, I mean that they're homeomorphic as simply, so geometrically they're homeomorphic. So for example, if your hypergraph is just an edge, say a 3-edge, so triangle, then of course you can subdivide this triangle in say this way, and this would be a collection of edges already, so 6 edges. These two are homeomorphic. So homeomorphic as simplicial complexes, and we are not going to use any fancy topology. So whatever intuition that you have for this, it should be sufficient for the talk. So let's first look at the case of graphs. There are these two theorems, both famous results from extremal graph theory, and I guess, well, the first one is one of the founding results. The first theorem tells us that if we look at graphs, so now these are the case of graphs, with no complete graph on R+1 vertex, then the maximum number of edges that we can have is roughly this, which more precisely is the number of edges in the balanced R-partite, complete R-partite graph. So you split your vertices like that, and then you do this thing. So this is the extreme. So say in this case, what we are forbidding is for R equals 3, we are forbidding this structure. Now, what does the second theorem say is if we forbid not only this structure, but all structures that geometrically look like this one, then the extreme is much smaller. It's just linear in n with some constant depending on R, which I don't want to talk about. And formally, this is this extremal number of n comma fr, where fr are all subdivisions of kr. So what are the subdivisions of kr? And this is kind of an example that's supposed to, I guess, help you with this homeomorphism notion from the previous slide. So this was our graph K4, and the subdivision of this graph is, well, just the same kind of structure, but with arbitrary number of vertices on each edge that subdivided. So this is an element in FR. And if we forbid all these structures, then, as I said, the extremal number becomes much smaller. So this is the case of graphs, well, since we are talking about geometry or topology, dimensional complexes. So one-dimensional simplicial complexes, objects that consist of the ground set and just pairs of elements. Natty Linial in the recent years was promoting this domain of high-dimensional combinatorics. It's not even a domain; it's more of a point of view on different, like a perspective on combinatorics, where, well, what he says is that in some sense, most of the combinatorial results are one-dimensional in nature, as graphs are one-dimensional objects. Many other results are one-dimensional, and he was suggesting to explore different higher dimensional analogs of these results. And one of the steps that in that direction that he was mentioning on several occasions in his talks is a three uniform analog of Mother's theorem. What very vaguely, what would happen? What would be the extremal number of, say, all subdivisions or all homeomorphs of a given, of the family of all homeomorphs of a given three hypergraph? So how many edges can a three uniform hypergraph have that avoids all those? And a particular question that Natty Linial was reiterating is this extremal number. Find the extremal number of the torus. What I mean by this extremal number of the torus is we're looking at all triangulations of a two-dimensional torus. And we are looking at the maximum number of edges an n vertex hypergraph can have, three uniform hypergraph can have, if it avoids all those triangulations. So this is one of the main questions that we'll be dealing with. Yeah, if you have any questions about the setup, then please ask, because this is the right moment.
I do have a little question. So I ban
Yeah.
all the triangulations of it. Wait, what is two torus? Just two-dimensional usual torus?
Just a normal torus. Yeah, I mean, I can yeah, cross out this. I'm just insisting that I'm talking on the fact that I'm talking about three uniform hypergraphs and two-dimensional objects. So in all the rest of the talk, this is what I'm concerned with. But torus you can define in any dimension. So I just want to make sure.
Well, I'm just a bit confused because there is plenty of triangulations of torus.
Sure.
So
this is the same. You know, if you think of the previous example, there are plenty of subdivisions of KR, and this is exactly the point.
But here, these subdivisions of KR, they are like simply, they are all just
it's a class that is much easier to understand. If this is what you.
So I just mean, if I what is triangulation of a torus? You just pick up a square and you make a graph like in the interior of a square, and then you identify its sides, the sides of the square, and you have a graph on the torus. So basically, I can draw.
This is the standard way of gluing a torus, and then you, of course, you just triangulate this somehow so that it is actually a triangulation. I mean, I'm not sure that what else. I mean, something like that. Yes.
Yeah, exactly. And so
it is a class that is difficult to deal with, and this is exactly the point of Natty. So one has to work with it more geometrically in some sense. So it has certain clear geometric property. A torus is a torus, no matter how you triangulate it. It has its features. And on the other hand, it is difficult to understand all these triangulations, even though there is a relatively reasonable understanding of all triangulations of a torus enumeration, and I'll come to that. So you'll see how one can deal with these kinds of objects. Okay, but yeah, we are forbidding all triangulations.
Okay.
Great. So any other questions? Okay. So here, the first question that I would ask at this step, if one haven't seen this problem, is why torus? Because there is a sphere. And the reason is, for the sphere, the problem is solved. It was solved a long while ago by Brown, Erdős, and Sós, who actually showed that this extremal number for triangulations of the two sphere are all, for the triangulations of the two sphere can be all forbidden when the number of edges is slightly below n to the 5/2, and some of them would appear if it's slightly above n to the 5/2. So the extremal number is up to a constant is n to the 5/2. So why is that? Let's see the proof. The more interesting part for us would be the upper bound. So let me start with the upper bound. Upper bound. So one notion that we'll need is the link graph. So L of V for V from our hypergraph. We fix, of course, a hypergraph, say hypergraph H on n vertices, and we're searching for this sphere. So the link graph which is all pairs U W such that V U W belongs to our hypergraph. So basically, you look at pairs of vertices that together with our vertex form an edge in our hypergraph. And the main point is that when the number of edges, which I'll denote by this, in our hypergraph is, well, bigger than some constant n to the 5/2, then we have vertices V and V prime, such that the intersection of their link graphs contains many edges. So the size, the number of edges of this thing in this thing is bigger than n. By this I mean just number of edges. So there are more than n pairs of edges, such that if you add to them both V, either V or V prime, then you'll get an edge from the hypergraph. This means that you have a cycle in this thing. And this actually gives you a sphere. Why? Or more precisely, it gives you a double pyramid. So this is what we call a double pyramid. So you put your vertex V here, you put your vertex V prime here, and here is your cycle in the graph. This is LV intersection LV prime. So this is your cycle. And now you have all these triangles. And the same on this side. Well, I guess it should be convincing enough that this is exactly a sphere, right? Any questions about this? So getting a cycle in this intersection of two link graphs gives you a sphere, and this double counting here is extremely simple. I mean, anybody who knows what double counting is would be able to repeat it. The lower bound, there are two ways to do it. In the case of the sphere, I'll present you one way that would be useful for the other cases. It's basically a probabilistic deletion argument. So what you would do is you would take a random hypergraph with probability of the edge roughly 1 over square root n. And then you would look at the expected number of the triangulations of all sorts of the sphere in this thing, and you'll find out that the expected number is relatively small, smaller than the number of edges, and then you'll just delete one edge from each such triangulation, and you'll get a new hypergraph with roughly the same number of edges, but with no triangulations of the sphere. So standard probabilistic deletion, one needs, I guess, two ingredients for this. First thing is we need to have some kind of control of the thing, number of triangulations of the sphere on, say, T vertices. And this is well understood. There were works by Tat, who actually gives an exact formula. And I guess the up to relabeling this number is exponential in T, and this is enough. So it's some constant to the T. So this is the first thing that you need, number of triangulations. And the other thing that you need is, well, you need to somehow bound the number of triangulations, expected number of triangulations of a given type. And what does it depend on? It depends on number of vertices, and it depends on the number of edges. So the more edges it has, the less probability it has to appear in a random hypergraph. But the more vertices it has, then the more potential copies that you have. And here we use Euler's formula, which tells us that for any triangulation, the number of faces is equal to the number of vertices minus 4 for any triangulation of S2. And these two things are enough, and then you substitute all of that in this deletion argument, and then you get it. So for each particular triangulation, you know what would be the expected number, n to the number of vertices times p to the number of faces, and you know the number of triangulations. You multiply by this for any given number of vertices, and that's the proof. And this proof would generalize, unlike the original proof of Brown, Erdős, and Sós, who used something else. So great. So this case we know how to deal with. Then let me say one more thing about the history. So recently there was this result of Keevash, Long, Narayanan, and Scott, Jason Long. So there are two people at Oxford. There were two people at Oxford with working in combinatorics with name Long, and they got they didn't quite get 5 halves, which we would expect for any actually a hypergraph, but they managed to prove a very general result. They get a universal exponent, this 1/5, so that whatever hypergraph you take, and then you take a class of hypergraphs homeomorphic to it, and then you forbid this class, then the number, this extremal number n, and this class of hypergraphs is at most n to the 3 minus this constant. So the main point here is that this is independent of h. It is easy to get a result for of the same form where this constant would be dependent on h. So getting something like actually, sorry, this is not theta, this is big O. I'm very sorry. So we don't have the lower bound, and we expect that this is 5 half, but they proved this upper bound. So easy to get that this extremal number is at most big O of n to 3 minus some constant depending on h, where this C of h is bigger than 0, using the result of Erdős, which says that extremal number of n k r r r is big O of n to the 3 minus some constant depending on R, where again this constant is bigger than 0. So this is just a complete tripartite 3 graph. Maybe I should put 3 here. So this is a result due to Erdős. And well, how can we use it? Well, actually, it's easy. Every hypergraph has a tripartite homeomorph using a barycentric subdivision. So what we would do is, if we start with an edge, we would do exactly the same thing that I was drawing already. We would put one vertex for each face, one vertex for each 2 edge, and one vertex for each vertex. And now we'll triangulate. And now it's easy to see that this thing, I mean, and then we'll repeat the same thing for each edge. And now it's easy to see that this hypergraph is tripartite. So this is the vertices form one part, the edges, the vertices in the middle of the edges form the other part, and vertices in the middle of the faces form a third part. And yeah, so this is a tripartite hypergraph. And of course, you start with your H, you do a subdivision. It would be some, finite hypergraph. So clearly it embeds into this one for some R, and then you can get this constant. But okay. So now this is our main result. So we actually get the right exponent, and not only the right exponent, but really the right asymptotics for any orientable surface. I mean, for those who have a little intuition about this, we'll get back to that. So we answered the question of Nati in particular for the case of the torus, of course, because torus is the second orientable surface after the sphere. This orientable is quite intriguing, and then I'll also get to that a bit later. So let's see a very, very rough sketch of how we do that, and then I'll try to illuminate some of the details. The proof is very different from what Keevash, Long, Scott, and Narayanan and Scott were doing. Their approach was not would not be working beyond E-1/4, I think. So the proof is more geometric. The main thing is the proof of the upper bound, actually, because, well, so the lower bound is really the same as before, except we need now to bound somehow the number of triangulations for any surface, for any fixed surface. And this was done more or less, I mean, to the precision that we need, this was done. So we use generalization of this result of that. And again, there is an analog of Euler's formula, which is actually even more advantageous for us in this context. For the torus, for example, it would look like the thing that we need is that F is equal to 2V. So the number of edges becomes bigger. So what about the upper bound? So the first thing that we do is we find a subhypergraph of our hypergraph that is saturated with these double pyramids, that the thing that we found for the sphere. So this double pyramids would be all over the place. I'll go back to this later. What do I mean by saturated? So once we have this saturation with double pyramids, we find a cycle in our hypergraph, what I call the topological cycle. And what is a topological cycle? So this thing is similar to a tight cycle. except there is more freedom. Let me draw you an example of a topological cycle. So something like this would be a topological cycle. So all these edges here. So for those who know the definition of a tight cycle, it's very similar, except we're allowed to turn more than kind of twice, to use one vertex more than well, 3 times, I guess. Or, so we can turn around one vertex for a while and then move to other vertices. So for example, this vertex is used in too many edges for a tight cycle, and this as well. So we find such, and then somehow we glue double pyramids along this cycle. So somehow you should imagine that around this we start gluing this double pyramids so that it becomes a torus. So this is a very, very rough sketch. So the picture that we'll get would look roughly like that. So these are these double pyramids glued along the cycle. So I'll specify in a second what do I mean by gluing along the cycle. The colors here are just for convenience. So what do I mean actually by gluing along the cycle? So let me zoom in on a piece of our cycle. So imagine that our cycle is like that. Maybe it's just where we zoomed in on a piece of our cycle. And what we do is we glue one sphere to this thing. So you should imagine a sphere kind of sticking out here. So we glue this sphere, then we glue another sphere to this thing. So to every 2 consecutive edges, and that you should imagine going down. I'm really afraid that I'll ruin the drawing, but let's see. So we glue it there. And then you continue. So yet another sphere you'll glue here along this 4 cycle, and so on and so forth. And it forms, if you of this, it forms this kind of a tube that is a bit zigzagging, and it goes a little bit like that. This kind of tube. So you should think of, you're entering through this edge, then you're exiting the red part through the other edge, and then you're entering the green part, you're exiting it like that and enter the violet part, and so on. So it forms a tube, and eventually this tube closes up. So this is the intuition for what object that we are actually constructing. Great. So this is, if we go back to this step, this is kind of the explanation for the gluing, but we still have lots of points here to understand what is the saturated and what is this topological cycle, and actually get a torus, and so on and so forth. So let me elaborate on some of those. So what do I mean by this saturation thing? I mean that we select a subhypergraph in which all edges, or more precisely, all pairs of edges satisfy a condition which is very similar to the condition that I'm defining on this slide, which is called this P epsilon K admissible. And let's see what is this P epsilon K admissible condition. So it is a condition for 2 edges. We have one edge and another edge that share 2 vertices. So x, x prime, y, z. This is our situation. And then we call this pair of edges P epsilon K admissible if for a unit set W, which is chosen by flipping a coin for each vertex with probability P, so a standard P random subset of our set of vertices, a certain event happens with high probability, with probability 1 minus epsilon. So again, this is just including each vertex with probability P independently of the other. We form a set of vertices that is random, and then a certain event happens with high probability, which is encoded both, like P is encoded here, epsilon is encoded here. What is this event? This event A that should happen is we're looking at the same graph that we were looking before. And so we take this vertex X, we take this vertex X prime, and then there is this graph G that is the intersection of the link graphs of these two vertices. So all edges that are connected to both. So we look at this graph G. So here is our graph G. Now we look at the part of G that is induced on W. So we restrict ourselves to this random set of vertices. And what we want there is that basically our two other vertices that we had this vertex Y and Z that were, by the way, connected by an edge, of course, because X, Y, Z was an edge. Things we want to be connected by many vertex disjoint short path. So this is a thing that we want to see in our graph. Lots of vertex disjoint short path between these two vertices. Of course, Y and Z may not be included in this random subset, and then this we condition on this thing. So we condition on this the fact that Y and Z are included in this random subset, and then with high probability we want to see this many vertex disjoint short path. And the intuition there is that basically each of these short paths, or each pair of this short path, can be transformed into this double pyramid. And then what we have is that we have so many of those things that even if we start to construct our, this image that we had before, like step by step, and then we use them on previous steps, we can exclude them and still we have enough paths to continue the construction. So this is the idea of the saturation here. So yeah, the main point here, I guess, is that we want to find, roughly speaking, some robust, very robust version of the statement that Brown, Erdős, and Sós were using. So not just one double pyramid, but lots of double pyramids that can be guaranteed even in random subsets. And so this is for the notion of the saturation. And probably this is one of the more technical parts of the proof. The other technical part of the proof is this theorem, but interesting on its right, is this theorem that guarantees the existence of topological cycles, basically, in sufficiently dense hypergraphs. This is the only thing we need, that we can find a constant length topological cycle in our hypergraph. So we have this structure to which we can glue our spheres, and it's not so easy actually to get. It required some work to get some result to use here. So it's not straightforward because they sent to the there is a similar conjecture of Conlon for tight cycles, and it's not known. There is also an unpublished result of Verstraete, who claims that n to the 5/2 is the threshold for a cycle of length 24. But we didn't want to rely on an unpublished result, so we proved this, and somehow topological cycles are easier to get than tight cycles. Great, so this thing guarantees us.
Sorry, Andrey, maybe I didn't get this one. So are you saying that the same bound is conjectured for tight cycles as well?
Yeah, I mean, up to, yeah, maybe here this should be C. Yeah.
Okay, yeah.
Yeah. Great. So we have our cycle, and then we have our notion or robust subhypergraph with these spheres, these double pyramids all over the place. So we can do this gluing. Then the other problem that arises is, well, how do we judge which surface did we get? Because I mean, topology is tricky, and one has to be careful about these things. And the main question actually here is it a torus or a Klein bottle? Because it's not so easy to distinguish. So let me give you a very quick recap of what do we know about surfaces. So we know that surfaces are either a sphere, so closed two-dimensional manifolds, spheres with G handles. So this is the following thing. So yeah, this is one handle, and well, let me draw another handle. So spheres with G handles, and of course torus is a sphere with one handle. So it's either so it's a sphere of G handle or sphere with so to say G cross caps, where this cross cap, what does it mean? So we have our sphere. We cut out a disk. So for one cross cap, we cut out a disk, and instead of this disk, we glue a Möbius strip to it. So this is, I don't know how to draw it, but there is no way to draw it in R3 in any case. So the point is that you glue a Möbius strip to this disk. You know, Möbius strip has just, the boundary is just one curve, and then you can glue it. And then this is the orientable case. This is non-orientable case. How do we distinguish those things? So we have this Euler characteristics. So here we will have number of vertices minus number of edges plus number of faces is twice minus 2g. And here we have v minus c plus f is 2 minus g. So the first thing, of course, to do in our case is check that it is a manifold, meaning that every vertex of the triangulation, if you look at all the simplices containing it, they form a disk. And that's not difficult to check. The construction is quite transparent locally. Then we can find the Euler characteristics. And Euler characteristics in our case is 0. So 0 means either a torus or a Klein bottle. So G equals 1 on the left or G equals 2 on the right. And then it's actually, yeah, we were quite a bit confused about this orientation things, but then we figured out what is, how to get the orientation from this topological cycle. It somehow depends on the structure of this topological cycle. Because there are these turning vertices, not just a tight cycle. For the tight cycle, it would be easy. It's like even length is orientable, odd length is non-orientable. But for this topological, in any case, after thinking for a bit and being confused, we realized that we have a tripartite hypergraph. Then can only get, well, I'll write it torus-like cycles. So we can get only tori in the, surprisingly. So there is no way to construct a projective plane or a Klein bottle along these lines, trying to find this topological cycle and gluing gluing the spheres on it. So it's quite surprising. Well, I'm not sure that I'll have time for this, but I'll just mention a little bit this thing. So how to glue more complex orientable surface? So how to get a pretzel out of how to get the pretzel and not just the torus. And well, the idea is that, well, what can we do if you have two tori and you take, say, two triangles on the boundary, then you can cut out these triangles and just merge these two hypergraphs, glue them along this triangle, and then remove it, and then you'll get the pretzel here, kind of. So currently, we can do a much more general statement of this type. So you take any two families of actually are uniform hypergraphs, and what you would do is exactly that. You take any pair of, I have to explain you, I guess, this sign. So now I'm talking about this part, and I have to explain you this sign. So it means basically F1 plus F2 for every F1, F2, and this is how we construct this family. And then what does it mean for given two hypergraphs? We just literally glue F1 and F2 along an edge. So in a graph case, for example, if you would have a graph like that, this is your edge that you want to glue along, and you can choose these edges actually. And this is, say, another graph. If you want to glue along this edge, well, what you would get is exactly what you expect. So, and here is the, you can do it for hypergraphs. I don't want to give you a formal definition of this thing. So basically, this is our tool for proving the result for any orientable surface. We take tori and then inductively glue them together, and this result tells us that basically if before we had upper bound n to the 5 halves, then we will stay with the upper bound n to the 5 halves. And the proof of this statement is very easy, and it's a very elegant. It's easy, but it's a very elegant probabilistic argument. Yeah, I don't think that I'll have. How much time do I have actually? I have maybe like 1 minute left or something.
No, I think it's fine if you talk for 5 or 10 minutes. It's fine.
Okay. So then maybe I'll try and actually quickly. The idea is to use this notion of richness, which is very similar to what we saw for the double pyramids. So we call an edge in our hypergraph f rich. It can have a bunch of parameters, but I simplify it so you can imagine 1/2 being written. So this edge is f rich if a random subset W of the vertices, and here random I mean uniformly random, so each vertex taken with probability 1/2, independently of the other. So a random subset conditioned on the fact that it contains E contains a copy of some f from our family that has E with probability more than 1/2. So with probability more than 1/2, if E finds itself in this random subset, then there is a copy of a hypergraph from our family F that with this edge E. So E belongs to this W, therefore E belongs to some F, which is from our family with probability bigger than 1/2. And has a copy of F, and then this copy, of course, F lies in W. And then it turns out that almost all edges over our hypergraph are actually F reach. So if we assume this lemma, that so it's like almost all edges are F reach, then what do you do? What do you do in this case? You just take an edge. You take an edge E that is reach. So, like going back to the previous statement, there we had there we had two families, F1 and F2. So you can take E that is F1 reach and F2 reach. So you take this edge because almost all are F1 reach, almost all are F2 reach. Then color V of H in red, blue. And then with probability bigger than 0, you'll find the red copy of F1 from the first family and blue copy of F2 from the second family. That both contain E. This is the definition is made for this. So a random, of course, if you color randomly in red and blue, then the red vertices would form this random subset W, and then the probability that E is contained in the copy is bigger than 1/2. And then the same is true for the blue subset. And again, the probability is bigger than 1/2, and thus with probability bigger than 0, the intersection of these two events is true. And this is exactly what you want. You just get two vertex disjoint copies of, well, one hypergraph from the first family, one from the second family. And so together, they give F1 plus F2. So this is how this works. And as for the proof of the lemma, well, okay, so this it's so maybe I can say something, but basically what you do, you look at all the bad edges, so the edges that are not reach, and then you pass to a random subset. And on this random subset, you form a hypergraph that consists of all the edges that are not contained, that do not contain a copy from F. So you pass to a random subset and you look at all the edges that are not in the copy, that are not in the copy of a hypergraph from F. And then somehow, because of this negation of the richness, these two things are very well related. So this hypergraph, on the one hand, cannot have size more than the extremal number, because any hypergraph with more than extremal number of edges would have a copy of F. But on the other hand, their sizes are related because, well, if edge is not F reach, then, well, it survives with a certain probability, and also most likely it is not contained in a copy from F. And so you can relate these two things, and this allows you just to estimate the number of not F reach edges. So it's in a way it is kind of straightforward, but yeah, one had to find the right perspective on these things. So yeah, I'm not sure how much this explanation was clear, but okay, I don't think that I'll go into the details. Unless you'll ask later, maybe. So yeah, let me finish with this slide. I just remind you that the main result that we proved is that we can get any orientable surface in a hypergraph, tree hypergraph with omega of n to the 5/2 edges, which answers this question of Lineal in particular. And I'll mention two questions for future research. One is, which is very intriguing, can we get a proof of the projective plane? Can we guarantee a projective plane in a hypergraph with that many edges? Somehow our approach doesn't seem to work. It only gives disoriented surfaces, surprisingly. This, of course, would imply any non-orientable surface. This argument with gluing things together that I kind of semi-sketched on the previous slides. Other thing is, which is also very intriguing, is what happens in higher dimensions. And here, so instead of 3 hypergraph, let's look at 4 hypergraph. And here, even the sphere is, it seems to be a difficult case. Even sphere, for that we don't know. We don't know the threshold. So this double kind of you can come up with this generalization of this double pyramids, but somehow the lower bounds are becoming harder, and it's unclear if this is the right thing. So yeah, I think I'll stop here. Thank you.
Thank you, Andrey. And could I ask everyone to unmute themselves and thank Andrey for this very nice talk.
Great, thanks.
So please, if you have any questions, then I think it's a good time to ask them now. So one obvious question would be if you can say anything about higher dimension, at least some, you know, whether you expect there to be a gap in the exponent of 1/2 always, or that gap getting smaller or bigger with n.
So we can say some things. I think no, the exponent should get smaller and smaller. It should be roughly like 1/2 to the r, 2 to the r minus 2, maybe. I don't know. Where r is the uniformity, and you can use this double pyramid argument somehow inductively. You know, you look at the intersection of the link hypergraphs of two vertices, and then it has sufficiently many edges under certain conditions, and then you find a sphere in that hypergraph. So, but this would get this kind of bound, and I think the lower bound, we're thinking about this, and then we can get some kind of lower bound which is not that far from this. I'll say n to the r minus 1/2 to the r. I mean, I'm writing roughly. Maybe I should write 2 here so that it matches at least the construction. And then I think we can get something like n to the r minus r over 2 to the r minus 2. So yeah, we can get something, but yeah, we're thinking about this.
Mm-hmm.
And for the other surfaces is really it's unclear. But that we have.
Right. So I don't know much topology, but this 2-dimensional case is very special, that you have this very simple classification. Nothing like that is possibly in a higher dimension, or am I wrong?
No, that's true. That's definitely true. And I guess that eventually one has to take some more combinatorial approach. This, if one, yeah, I don't know if one hopes to solve this problem, even for 3 hypergraphs, there are lots of other hypergraphs, and then this say result of Keevash long Narayanan, it has a purely combinatorial approach, and maybe something along. Maybe something in between our and their approaches, which doesn't use that much topological knowledge, would work. But definitely we cannot rely on topology so much. Maybe for the lower bounds, we have some kind of understanding of certain invariants, and this would potentially would give us some bounds along this probabilistic deletion argument. So for the lower bounds, we can hope for that, but I think for the upper bounds, one needs to have a more combinatorial approach. But again, I'm not even sure that this opinion is shared by my co-authors, so I don't know.
Okay, thank you.